Well, this time we're going to take a little time for a review of basic concepts and terminology, and then we're going to look at a special case for the power rule. So over here on this slide, I've just kind of showing, and we'll go through what we already have learned. And when we came up with the concept of a derivative, we used a discrete representation of the derivative in order to show that we get the some of the rules that are basic to differentiation. We did the same thing with integration. We had that the area, we could express the area under a curve x squared as the sum of, well, for an individual value of x sub I squared times delta x, and this would be the width of the base of a triangle. In the limit that delta x goes to 0, that's basically equivalent to the integral from 0 to x. So this would be a definite integral of x squared dx. And we already know, just applying that power rule that we've already talked about, that and that we developed using this discrete notation, discrete approximation. We get x cubed over 3, but we have to evaluate it at these two limits. So we get big X cubed over 3 minus little x cubed, which we didn't show here because x is equal to 0, so that second term is disappeared. So is 0. So the typical integration problem is expressed where the integrand is the derivative of something, and the result is what it was that you had to differentiate in order to get this integrand. So that's all that integration is, really. So we have a y prime, in this case a derivative, which is equal to x squared. We want to figure out, in other words, take the integral of x squared to figure out what it was that we had to differentiate in order to get the integrand here. And here we show our result. We add in this constant c, because when we go through this differentiation process, we're going to get x squared, but we have no idea whether there was a c in there, what its value was, whether there was not a c in there. We have no idea. So we have to indicate, at least in a general sense, that there could have been something in there. So this is a definite integral here because we have the limits of integration defined. This is an indefinite integral because we don't have any limits, and we just put in this constant c here to cover a general case. And so what we've gone through up here, and the rules that we've been applying, follow this basic rule of integration, which is that if you have an integrand which is x to some power n, we raise the power by 1 to get n plus 1, and then we divide by that new power. And of course we have to add in our constant of integration. Okay, so let me ask you, well, what are we going to do with this integral here? We've got the integral of x to the minus 1 dx. What's going to happen here when you apply the power rule to this? If we go through that, we're going to increase the exponent by 1 and divide by the new exponent. Maybe pause for a minute before going on and try to work through this. So having taken this to heart and worked it out, you will have seen that you get x to the 0. Applying our power rule, we get x to the 0 over 0 plus this constant. Well, again, just x to the n plus 1. We get minus 1 plus 1 is 0 over minus 1 plus 1 is 0. So we have x to the 0 over 0. And going through this representation here, it's just not working for us because 1 over 0, that's not very satisfactory. That doesn't tell us much. This is where, when you run into problems like this is where knowing as much as you can about derivatives is really helpful in undertaking integration, because we know that the derivative of the natural log of x is going to give us 1 over x. So we know what our result should be already. And we just abandon that power rule in this case because we know from previous experience working with derivatives that the integral of 1 over x is equal to the natural log of x. And again, this is an indefinite integral, so we put our constant in there. Now, looking at this graphically, it just kind of emphasizes the point, and making use of graphs is always useful. This is the log of x. We can see that it looks almost like an upside, mirror image of 1 over x. But more importantly, when we look at the slopes of the natural log of x, we can see that they start off really, really high, and that they drop as we come to higher and higher values of x. So this relationship we've already talked about before, and we use these general ideas in order to kind of develop conceptually the relationship between the derivative, in other words, how the slopes vary on the log of x, and the function 1 over x. Now, we also spent some time going through the discrete computation of an area. So we have a function like 1 over x. If we wanted to figure out what the area under this curve is, we could evaluate 1 over x at x sub I, multiply it times the width of an individual rectangle. This would be the height x sub I for I equal some arbitrary value, and then just sum them all up. So we have all the rectangles shown here. It's a lot of work, but if we do this over the integral, so this would be a definite integral over the range 0.1 to 3, the approximation using a delta x of 0.1 yields an area of 3.37. The exact computation, the result, the natural log of x gives us the log of x2 minus the log of x1. Remember, it's a definite integral. We're evaluating it at the limits. And we could also rewrite this as the log of x2 over x1, which in this case would be equal to 30. In other words, we have 3 divided by 0.1. We take the natural log of 30, we get 3.4. In other words, we have to raise 2.71828 to the 3.4 power in order to get 30. That's for a delta x of 0.1. We could improve on that using a delta x of 0.01. We would get 3.4008. And that's actually, if we round off, this would be 3.401, which would be identical to the analytical result that we obtained by taking the difference of logs, which is 3.401. 3.4008 rounded up 3.401. So we're right on the money here, but this is a lot of work. So being able to do this analytically, do it explicitly, is really makes life simple for us, because you wouldn't run around doing this for every function that you ran into. You'd be spending your life on Excel, when we could do this actually pretty quickly. So, but take to heart this visual representation of what we're doing. Basically, when we do this integration here, we're calculating the area under this curve. So let's take a look at a couple of examples. We've got the cosine of theta d theta, and a little bit more complicated example. A good time to pause, maybe work through these. Well, the first one, not much work to do there. We're just kind of relying on our recollection. We could go back to the graphical relationship of slopes that we had talked about, but we know that if we differentiate the sine of theta, that we get the cosine of theta. And that's always what we're doing when we go through an integration. We're trying to figure out what it is that we had to differentiate in order to get this integrand. And in this case, it was the sine of theta. And of course, we had to add a c in there because when we differentiate this, we could have any value of c, we'd still get cosine of theta. Now, in this second integration, we said that, well, this integration operation is distributive. We can just take that integration operator and distribute it through those terms. So we have the integral of e to the x dx plus 20x to the 19th dx minus the integral cosine x dx. And so looking at those term by term, we know that this is kind of indestructible function under differentiation. It's also that way under integration, integrated over and over and over again. And well, if we include the constant in there, things do change. But we get e to the x plus c1. And here we get increase the power by 1. We get 20. Divide the integrand by 20. That removes the 20, so we get x to the 20 plus our constant. And we have the integral of the cosine again, which we already know is the sine. In this case, we're using x instead of theta. And so putting all the results together, we had all these different constants, c1, c2, c3. Well, e to the x plus c1 plus x to the 20 plus c2 minus sine of x plus c3. Just combine all those constants together. And that gives us e to the x plus x to the 20th minus the sine of x plus c. So that would be your result. So let me give you a couple more examples. Here's an integral of a sum of powers, basically powers of x. So this should be an easy one. You could break this up into 3 separate integrals, but we've done that. We know what's going to happen. They're going to get summed back together. So we're going to get a single constant. So why not just evaluate them as we see them? The first term will be x to the 4th, multiplying the denominator by 4, we get 12. And for the next term, x cubed over 6. And for the next term, increase the exponent by 1, x squared divided by 2, the new exponent, and add in that constant. Here's another one, 1 over x plus x squared. So we've got a couple rules that we need to use here. We'd use the power rule for this term, but we have this special case that we use for x to the minus 1. When we do that, hopefully you got the log of x for the first term plus x cubed over 3 for the second term, and then there's our constant of integration. Okay. For the next time, we're going to move on. We're going to look at, we differentiated exponential functions. Now we're going to integrate them. So you might want to review these general rules. And for the next time, we'll talk about the evaluation of, this will be an indefinite integral, but it could easily be a definite integral. And so we'll cover the rules for integration of exponential functions and talk about some additional rules and examples. So see you next time.